In this video, I'll talk a bit about the expected values that variables can take under seeing other variables, so seeing the value of other variables, or maybe even doing something in the SEM model or something in the system, so intervening on the model. So if the SEM model fits, of course that's important. If the SEM model doesn't fit, then your model is not good. So all these kind of derived things are meaningless in a sense. But if the model fits, we can, of course, look at all these conditional independence relationships, but we can also look at the predictive effect. So what we predict would happen, and the causal effect, what we predict would happen if we intervene on something. So the predictive effect is the expected value of y, let's say like some outcome variable, right? It could be in a set of variables as well, could be multivariate. The expected value of y after we see that x takes some value, and let's call that value z. Right, a bit of a weird notation here, but we say let's say that x takes some value z, so x is a random variable here, but z is some observed outcome. So let's say after we see that this value takes some sort of value, the expected value minus its expected value without conditioning it. So how much more do we predict? How much higher is our prediction of y given compared to our previous prediction of y after we now also condition on x. The causal effect is the same, but now we use this do operator. This says how much higher do we predict y to be compared to what we predicted before after we set x to z. Now in SEM 2, we're ignoring the mean structure again. We included it in SEM 1 in week 3, mainly for linear growth curve models, but also mainly for invariance testing. So basically this will just always be 0, right? So yeah, we can ignore this because the expected value of our variables is 0 in this case because we're assuming everything to be centered. Or we can assume this to be mu, for example, but we can ignore it, right? So in SEM 2, we won't really talk about this. You can compute it, of course, as well, if you want, and you have a mean structure included in your model. So for simplicity, we'll assume that these expected values are 0, and that will simply make this predictive effect the expected value of y after seeing x take some value, and the causal effect the expected value of y after doing x, setting it to some value. All right, so how do we compute this? Well, we can get the predictive effect from the conditional Gaussian distribution, assuming again that everything is centered here. So the expected value of y after seeing that x takes some value takes this form, very similar to the shear complement, right? That's the covariance of y with x times the inverse of the variance times z. And if these are all single variables, so if you have univariable questions here, then it becomes a bit simpler because this inverse we can just write as over x. So this is the covariance of y with x divided by the variance of x times the outcome value of z. Right, so what we see x to be. And this we can quite simply compute, right? If we have these variances and covariances, which we can get from our sigma, or we can get from our path tracing rules, we can compute this. All right, so let's look at an example. So let's look at the predictive effect of x on y2. So the predictive effect of x on y2. So let's say we see that x takes some certain value. What is then the expected value of y2, right? So normally the expected value of y2 is 0 because we assume it's centered. So what's the expected value now? And then we can compute that. So we have the covariance of y2 with x, right? So let's use the path tracing rule. So we take one step back, we take a double-sided arrow here, and we're there. So that's beta 2 times beta 1 times the variance of x divided by the variance of x. Well, one thing you will see here is that this is simply cancels out, right? So we're left with beta 1 times beta 2 times z. So that's the expected value of y2, given that we see x takes the value z. All right, let's do another one. the predictive effect of Y1 on Y2. The expected value of Y2 given that we see Y1 is set. Alright, so we can do the exact same thing. So what's the covariance between Y1 and Y2? Right, so that's actually a bit more tricky. So let's see Y2. Well, we go back, right? We're at Y1, and then we can take this double-sided arrow and we're there, right? So we have beta 2 times theta 1, that's this part here. But we can take another path, we can go back even further, take this double-sided arrow and then go forward. There's nothing against that, but we don't need to stop here, we need to go back, take a double-sided arrow, go forward. So we have beta 2 times beta 1 squared, because we go 2 times over this thing, plus the variance of x, right? So that's the covariance between y2 and y1. And what's the variance of y1? Well, that's beta 1 squared times this times, right? Beta 1 squared times the variance of x plus this residual here. So now we can see here that this says beta 2 times beta 1. Well, this is the same thing, right? So this is just beta 2 times beta 1 squared variance of x plus theta 1. Right, and that cancels out. So that cancels out there. So then we're just left with beta 2. So we have beta 2 times z. Now the predictive effect of y2 on x. So what's the predictive effect of knowing y2 on x? Right, and then we can do the same thing, right? So we can compute the covariance, compute the variance, and then that becomes a bit more tricky. So we get this this expression here. I don't think this can be simplified any further, so that's just what it is. Now for the causal effects, there are two ways in which we can get the causal. There are actually multiple ways, but I'll teach two. I think the easiest way, even though it's a bit weird if you look at it at first, is by making a dummy model or a mutilated model, as it's sometimes called, in which we make the variable we intervene on exogenous. Right, so let's say we have, let's say A causes B causes C, yeah. But now we're going to say expected value of whatever, do B, do set B, do Z, for example. Okay. So we're going to intervene on B. Yeah. So now B is no longer caused by A because we caused B. Right. So what we do in this mutilated model is we remove this arrow here because we already know what caused B. And then one thing I do is I remove that, but I retain its variance. So I just write down its variance that we already had. So in this case, it was like this parameter times A, variance of A times that parameter plus some residual. We retain that temporarily because it also is going to drop out as well. And if we have that mutilated model, then we can just compute the predictive effect using this dummy model, this mutilated model. Right, so we remove all incoming direct arrows on the thing we intervene on. We put its variance that we had before there as well. And then we have the predictive effect as usual. An alternative is to calculate the total effect. And that is if we have a model, sometimes this is actually much more simple, but I'll show you the dummy model way just because it's, I think, a bit nicer. But if you have, let's say, A, B, C, and let's say there's also some direct path here, something like that, right? So we have, let's say, beta 1, beta 2, beta 3, and then we say A equals Z. What we can then do is list all paths from A to C using only unidirectional arrows, going only along the direction of the arrow. So one path is beta 1, beta 2, and the other one is beta 3. Then we just multiply that by Z. And then we add that. So we have beta 1 times beta 2 times z plus beta 3 times z. So that can sometimes be more fast as well. But if you have a very complicated model, then this will probably be easier. Okay, so let's take a look at that. So what's the causal effect of intervening on x on y2? Okay. So the dummy model is not different than the original model because x is already exogenous, right? So the total effect would be beta 2 times, there's only one path, so beta 2 times beta 1 times the value that this takes. And we already see that that's the solution as well, which is nice. But we can also take the expected value of the dummy model in the same way we did the expectation before. Right? It's the same formula. And then we see we get also the same result. So beta 2 times beta 1 times z. All right, so now let's intervene on y1 instead. So I can create a dummy model. So first thing I can do actually is show the total effect of y2 on y1 would simply be only this part, so beta 2 times the value y1 takes. So that's beta 2 times z in that case, right, if this is z. But we can also look at the dummy model. So what I do here is I create a dummy model where this s is removed because x is now the thing we intervene on. And the variance I retain. So I just put the variance of that here temporarily because it's canceling out because you're dividing by the variance anyway. So then we have this model. And then in this model, I can compute the expected value like I did normally. So I have the covariance between y1 and y2, right? So that's beta 2 times, and then this is the double-sided arrow, right? So times this, then we're there. That's beta 2 times this. And I have the variance, which is this as well. So that cancels out. And now I'm left with beta 2 times z. So that's then the causal effect of putting y1 to z. And that's quite powerful that we can do this in SEM because we can get an idea of what would happen under intervention, even though we fitted our model only on observational data. And of course, not only on observational data, also on theoretical knowledge because we specified the model, right? This is what we put in there ourselves. All right, what's the causal effect of y2 on x, so intervening on y2 on x? All right, so here, the dummy model is actually easy, but the total effect, you see that there's already no arrow, right? But the dummy model is also easy because we make a dummy model, so this one is removed. So this is just an exogenous variable, but it has no outgoing causal effect. So what's the causal effect of y1, 2 on x? Right, that's 0. We already know that because doing something here, there's no outgoing causal effect, so nothing is going to flow back to x. We already knew that. We don't need to compute anything. Of course we can, right? And then we see that that's 0. And now we can also do this in bigger SEM models, which is nice. So here I have a SEM model with 3 latent variables, 2 indicators each. I have all these matrices, right? And then we can do all this. This is really nice. So let's first look at these matrices. We need a few things. So we need to know, so for example, we need to know the covariance between like either 1 and y6 if we want to look at causal effect of this on y6, for example. Right, so we need to compute a few things. We can also use our path tracing rules for that, but that is used to matrices, so you also get a bit more experience with that. So we have our matrices, and then we have our expression, our SEM model expression, for the variance model of y, so that's a variance covariance matrix of y. That's called sigma. That's lambda times I minus beta, so I is identity matrix, right? 1, 1, 1, zeros. I minus beta inverse times psi times I minus beta inverse times the transpose of lambda plus theta, and we get well, these values, right? So an expected variance covariance matrix, where this gives me like the variance of y1 and the covariance of y1 with y2, etc. That we already know. But we can also look at some other things. So for example, we can look at the variance of eta. right? And the variance of eta turns out to be this expression. Yeah, and that turns out that comes from eta equals beta times eta, ignoring mean structure, plus zeta, which I can never really draw, right? So then we move this to the left, so that's eta minus beta eta equals zeta. Then we have I minus beta inverse, sorry, not inverse, eta equals zeta. So we have eta equals I minus beta inverse zeta, right? And then the variance of that equals, and then the variance of this, and then this becomes before and afterwards. That's a rule for matrix covariance algebra. So if I minus beta inverse times the variance of this, we call that psi, times I minus beta inverse transpose. And that's this expression here. We can just compute that if you want. And in the assignment, I'll show you a way that's I implemented in SEMplot, where you can do these kinds of algebraic expressions a bit more easy. So now we can use this already to see that we had this chain, right? So we had eta 1 causes eta 2 causes eta 3. And we can see that eta 1 indeed is conditionally independent of eta 3 given eta 2 with the Schur complement that we had before. We just fill in these values. So we have 0.18, that's this one. 0.6, that's this one. 0.41, that's that one. And 1.36 is this one. And we see that that leads to exactly 0, rounded to 2 digits. But that's because these are rounded to 2 digits. That's nice. All right, then finally, we can also compute covariance between the latent variables and the observed variables. Right, so that's the covariance between the latent variable and this expression of the latent variables. And then if you do the math, you get I minus beta inverse pi, I minus beta inverse transpose times lambda transpose. That's like part of the whole expression that we had before, and we get this matrix then that gives us covariance between etas, this eta 1, eta 2, eta 3, and the observed variable y1, y2, all the way to y6. Now we have all the things that we need to compute everything we want, really. Until we start making dummy models, that's of course important as well. So what's the covariance between y1 and y6, right? And we can just fill in these things in the Schur complement. And then we get, the covariance of y1 and y6 given eta 2, right? So we condition on eta 2. And then the Schur complement gives us exactly 0, which is nice. So this tells me that these are indeed independent of each other after conditioning on this middle part in the chain. Okay, what's the expected value of y6 given that we see y1 is 0.5? So what do we expect to happen here if we see this? Well, these are positive numbers, right, in this case, so we expect some sort of positive correlation here. So we expect that if we see that the person has a higher score here, then we do expect to predict the higher score there. Right, then we can fill in these numbers, and indeed we have some effect here, 0.2. That means that we expect that if we see that this person gave a response of 0.5, here we expect 0.2 higher than average on y6. Now, what is the causal effect of doing y1 is 0.5? So now we intervene on this and we say, no, we give you the response 0.5, right? On y6. Well, that you can think about. And if you thought about it now, then you might have already concluded that that is 0. Right? Because, well, we can make a dummy model here and we just remove that and there's no path anymore here, so that's clearly 0. All right. Now, what is the effect of y6 after we do eta 2 equals 0.5? And then we can make a dummy model. We can also use a total effect, which gives us 0.4 times 0.6 times 0.5 in this case. Or we can make a dummy model, so we have new matrices here, right? So psi, like a new psi now equals 0, 0, 0, 0, no, sorry, 1.36 here, 1, 0, 0, 0. Right, and the beta is a bit different, so we need to take it into account and recompute all the variance and covariance using the expressions, but we can do that. And then we can also compute the causal effect. Or we use this total effect, which is also, it gives us 0.4 times 0.6 times 0.5, because these two cancel out. And then we get 0.12. Right, so that means that in the weaning on the detained variable, it gives us an, when we set this to 0.5, then we expect this to be 0.12 higher, which is nice. Okay, and that's it for the video lecture on expected values under seeing and doing.